Thank you. Thank you, John, and thank you, Epifanio, for allowing me to speak about this. And of course, thanks to the Institute that actually this is a little work that I sort of worked out here. And it has been nagging me for some time. It's actually nearly a trivial problem, you will see. But it does have some importance, and it also is, to a certain extent, interesting and a little bit unexpected, as I hope to convince you. So the motivation for this little work is that, first of all, curiosity, and then fluctuations in confined geometry, they also depend on the surface interactions, and that can be used to measure parameters like surface anchoring, as I will show. And we did that some years ago, but in our measurements we also we always just neglected any effect of the viscosity on the backflow and consequently on the direction of propagation of fluctuations. So this is one reason why it was an interest for me to analyze this. And we also have, last year, got some measurements of fluctuations in a thin sample by a very different method, by looking essentially at the time correlations of polarized microscopy images, and got some results which were not in accord with what one would expect from bulk expressions for the fluctuations. And of course, it is obvious that to some extent backflow must be restricted when you have boundary a thin slab with boundary conditions of zero velocity. So I will first tell a little bit of how we can use nematic fluctuations, thermal fluctuations, in a thin slab to obtain the anchoring coefficients and also some other parameters. Then I will present the results of the calculation of black flow, essentially quenching. It's not completely quenched, as I will show, in a homeotropic sample, and how the relaxation rate depends on the transverse wave number. Then I will present the opposite geometry with a planar orientation, where the mode structure, that means, I'll show what I mean by that, is in an interesting way affected by the coupling to the flow. And then I will also present the results of what happens at finite anchoring strength and what happens in an external electric or magnetic field. So let me remind you how the orientational fluctuations in bulk look like. We have two branches of the eigenmodes, of the fluctuation modes. One is bent to splay when you change when the wave vector is in the direction of the director, it's always a bent mode, which goes to splay when the deformation is the perturbation of the director is parallel to the wave vector, or goes to twist with the deformation perpendicular to the wave vector. And of course, in an infinite space, all the wave vectors are allowed. In the case of thermal fluctuations, the amplitude of the mode is given by the equipartition theorem. This actually helps us to also get from the light scattering data to get the elastic constants, as I have also already shown. So the relaxation rate are a little bit more complicated. They depend both on the for bend splay mode, this would be the splay elastic constant. For bend twist mode, this would be the twist elastic constant and the perpendicular component of the wave vector, and they would always go to bend with wave vector along the director, which is in the z direction. And then we have some effective viscosity, which is a complicated, relatively complicated function of the Leslie viscosity parameters. this term is called the backflow effect because it comes from the coupling of the flow, and it always diminishes the rotational part of the viscosity. It's also worthwhile noting that the alpha 3 parameters is in all known cases much smaller than alpha 2. Alpha 2 is of the same order as gamma 1, and usually, well, in all practical cases, negative. Alpha 3 can be either positive or negative and small. So this backflow term for the bend situation, because alpha 2 is of the same order as gamma 1, and some of these viscous terms in the this is also of the order of gamma 1. So the backflow effect on bend is usually quite substantial, while on splay, even though it is also coupled, this alpha 3 is small, so on splay it's nearly negligible. So when one observes the different modes in light scattering, the direction and polarization of the incoming and scattered light actually determine which mode you're looking at. And you can, this is
neglects and multiple scattering. Neglects and multiple scattering.
Of course, we always need to. I mean, you can work with multiple scattering, but then the information is much less useful. So this is now how the angular dependence of the relaxation rate would look like in a bend splay situation, going from the z direction with the wave vector of the same magnitude to the perpendicular direction to pure splay. So in a typical values for Leslie coefficient, it has to be said that it's not very easy to find reliable values of the Leslie coefficients. Actually, they are well known only for a few cases, like the old MBBA and for 5CB to a certain so anyway, the difference between the elastic constants are of the same order of magnitude, while the backflow changes the relaxation rate. That means effectively decreases the effective viscosity by a factor of something like 3 or even more. So let me also remind you a little bit what one expects in the general case for any kind of waves in a confined wave guiding, one would say, geometry. For any field that is a solution of the Helmholtz equation, the free space solutions are of course plane waves, so that either the frequency of a propagating wave is given by the square of the magnitude of the wave vector, or the relaxation rate in case of overdamped, like nematic fluctuation, is also given by the square of the magnitude of the wave vector. But now, if you confine the waves in whichever dimension, then one of the components of the wave vector is going to acquire just discrete values, and there is going to be some minimal value with n equal 1, plus something of this magnitude, plus something which depends on the boundary condition. So there is going to be a minimal value to the confined component of the wave number, which means that any waves will require a gap at a 0 remaining continuous part of the wave vector. Actually, this is interesting. In a sense, this is a mechanism how you can provide mass to any kind of massless excitation by simply confining it in whatever dimension you have. So this allows us then, of course, to measure the anchoring energy. We have to ensure by the choice of scattering geometry that we are really looking that means going to small enough scattering angles and to choosing scattering vector so that it is perpendicular to the sample. Then we are looking at the fundamental twist, for example, twist bend mode, so looking at this kind of motion out of plane of the director. And then when you plug in the boundary condition, the mixed boundary condition for finite anchoring, you get a simple relation for the transverse component of the wave number. It has to satisfy this transcendental equation. Similar one will crop out several times again. And then for depending on whether you have strong or weak anchoring, this is how the amplitude of the mode, so this fundamental mode, looks like as a function of the transverse coordinate. And of course, it's simply given by the elastic constant of viscosity and a squared for strong anchoring. But for medium or weak anchoring, you also acquire a linear term in the thickness of the sample, from which you can determine the anchoring energy, provided that, of course, this effective viscosity is the same for the two parts, for the bulk component and for the surface part of the driving force. One can also add to the problem what happens when you have some dissipation at the surface. We've had an example of that, which we succeed, and that gives you again a separate constant to the relaxation rate from which you can determine this surface dissipation parameter. We had one case where we could interpret that in terms of some small, there was a photosensitive orienting layer, and this surface dissipation we could interpret as a layer of essentially contaminated nanometer-sized layer between the liquid crystal and solid surface. So the way we measured anchoring energy was simply taking a sample in a wedge shape, so that we can measure in the same sample as a function of thickness for either this would give us twist deformation. That means in-plane anchoring energy, azimuthal anchoring energy, or splay for the out-of-plane anchoring energy. And then we plot the relaxation rate as a function of thickness, and the linear part of this dependence on the thickness gives us the anchoring energy for strongly wrapped polyimide or nylon surface. You get something like standard value for the anchoring energy. If you only weakly wrap, then you get only linear part of the relaxation dependence on the thickness, with something like 10 times smaller anchoring energy. So this really shows that anchoring energy is really depending on how you prepare your surface. We can also then get the temperature dependence of the anchoring, and we did get the temperature dependence of the anchoring energy, which interestingly behaves essentially in the same way as the ratio of the elastic constants. So this maybe goes back to this question: what is the mechanism of surface anchoring of this? More properly, what the surface anchoring as measured through extrapolation length. This is obviously something that is, I mean, if you look at what the polyimide layer looks like, it's a partly oriented polymer layer, which is still probably the anisotropy. It can be measured optically, is very small compared to the expected anisotropy if all the polyimide chains would be stretched. So that means that you only have nanoscopic domains of polymer, which are just partly ordered. This partly ordered domains then propagate in a thin layer into the liquid crystal, and this is obviously mediated then by elastic the surface part of the elastic interactions. So this is why I think this ratio is nearly exactly the same as the ratio of the elastic constants. Anyway, so now this was all done neglecting the coupling to flow. So essentially assuming that the viscosity affects in the same way the bulk part and the surface part of the relaxation rate. This is certainly okay for the twist mode because twist mode is not coupled to the flow. And it's also more or less certainly okay for the splay mode because we know that the coupling of splay to flow is small. But it would be wrong for bend because we know that bend is strongly affected by backflow. And so since the boundary condition must affect the flow, the bend should also be strongly affected. So we have to start from linearized Eriksson-Leslie equations. The first one is, of course, the equation for the rate of change of the director, and the second and third are the components of the divergence of the dissipative part of the stress tensor plus the pressure term. So essentially what remains from the Navier-Stokes equation, neglecting the inertial terms and nonlinearities. And then we have also the non-compressibility condition, which also, of course, gives us the pressure term in the two equations. Now, in order to save some writing, we can introduce these two Mishevich viscosities plus another term which enters the viscosity backflow term. And so let's first now look at this most critical case of homeotropic orientation, so that at Qx of this component of the wave number being 0, we have pure bend mode. Then this can be approximately solved analytically. Then we don't need the pressure at all. The z component of velocity must be 0, and we are left with just two equations. You can integrate the second equation for the velocity and plug it into the first one, and then of course get a solution for the director in form of a cosine term plus a constant, and then plug it back into the velocity equation, and you get an expression for the velocity which has to be 0 at the boundaries, and then you get this transcendental, again a similar transcendental equation as for finite anchoring energy for the wave number, which you have to plug into the expression for the relaxation rate. And it turns out that a very good, surprisingly good solution to this transcendental equation is it's nearly 3 over a squared, just corrected plus this backflow term corrected by something which is close to 1. So when you put that back into the relaxation rate, I get that the relaxation rate there is a small correction due to the remaining part of the coupling to flow times 3 over a squared times this elastic constant divided by the rotational viscosity. And this is very close to what you would get by simply neglecting the backflow. This is pi over 2 a squared is 2.5 times 1 over a squared instead of 3. So there is some backflow effect still remaining, but it's a very small one, well, relatively small one. Now, what happens when you allow finite values for the x component of the wave vector? Then, of course, all the variables become plane waves in the x direction plus some times a function in the z direction. Then you can eliminate pressure in the x component of velocity from the Eriksson-Leslie equations, and then you end up with a system with a system of two equations which is of the 6th order. with boundary condition, of course, for n, with strong anchoring for n equal to 0 at the boundaries, and for the two velocities equal to 0 at the boundaries, so the z component of the derivative of the z component of the velocity has to be 0 at the boundary. And it's a little bit awkward system. So you take the, now you can separate the solutions into the even and odd solutions. The fundamental solution is going to be even, so the cosine of some wave some root of times z is the proper function, and q squared is a root of a third-degree polynomial, which you cannot really solve analytically. And then from the boundary conditions, you get a determinant of this form, which so of course this polynomial depends on the relaxation rate, so that you cannot really solve it explicitly. And then the relaxation rate depends on the solution for the q values that are satisfy this determinant equation that comes from the boundary condition. Now, it's a bit awkward to solve. I tried first iteration, that means just choose some value of the relaxation rate, solve, get the roots and put them into this transcendental equation. It doesn't work too well. What worked was that to express the coefficients of this polynomial in terms of the roots. Then you have 4 nonlinear equations that you can solve simultaneously, and that works relatively okay. Except one has to be careful that this one root is always negative and can be quite large. And the other two are sometimes real and sometimes complex, and this makes it a little bit awkward. So I choose some sort of standard values of parameters, realistic values. Then what you get for the for this bend splay case, this is this approximate analytic value of about 3k over a squared times gamma 1. And this would be what the bulk expression would give for the relaxation rate. So you see that is really what one would expect. This backflow is quenched for small qx, but then at larger qx, it actually the solution approaches the bulk expression. And if one looks at the profiles of the director deformation and of the velocity at some small finite value of qx, the x component of the velocity goes approximately like sine, and the z component is at small, goes to 0, of course, as qx goes to 0, and is quite small, but then grows. So nothing very unexpected here. Now, let's go to the other case, where we have, we start with the planar orientation, so for qx equals 0, we have pure splay. Now, the effect of flow quenching should be more should be larger at some finite qx value where we go from splay towards bend deformation. And indeed, when one solves the system of equations, it's the same system, just exchanging nx with nz. One gets this dispersion relation as a function of the transverse component of the wave vector, and when in order to get this, one has to be careful to choose either real or complex values to initiate the nonlinear procedure of finding the roots. And so I thought that this little bump here is first with some numerical problem, but then I plotted also what happens when you plot the second order mode. That means the mode that has this 0 qx one node in the middle, two nodes in the middle. This is a second order odd even mode. And one gets this sort of suggestive image. And when one plots then the third even mode, it's actually quite evident. It's sort of a mode interaction, a crossing avoidance, which is, as an afterthought, it's obvious why it happens. When one looks at the bulk expression for the relaxation rate, due to the fact that the relaxation rate at a given magnitude of the wave vector is much higher for the band than for splay, the relaxation rate for discrete values of the z component of the wave number that would correspond to the simple cosine dependence in the z direction, and using bulk expression, you get this picture. So the zero order mode increases due to being closer to the band mode at a given value of qx, is at some qx becomes larger than the second order or third order mode.
And
so
the existence of y direction doesn't kill this mode repulsion. You can see the two-dimensional picture.
Well, in the y direction you would go to the twist instead of to splay to twist mode, and the picture would be the same. I just don't. It's just that these crossing directions would have some
infinity of crossing.
Yeah. So it's actually there are sheets of dispersion relations, and which would cross without the flow cup, without the this backflow quenching effect. So it means the boundary. So this is again the same thing that shows this. So anyway, when one plots this bulk expression for the first mode and the actual expressions, actual results for of the calculation, you see that exactly at the point where this crossings occurred, we get this mode repulsion, which is kind of cute, I think. And one can also plot then how the profiles of the modes look like as you go from very small value of the wave vector towards through this crossing region. And you see that if you look at the director profile, it goes from a simple cosine-like profile, then gets somewhat deformed. Then obviously in the close to the crossing region, it gets a substantial contribution from the second mode, and then above the crossing it becomes the second mode. It means having two nodes in the profile. And similar picture you get for the velocity components. This is x and this is the z velocity component. At small qx, the z velocity component goes towards 0, of course, but we still have some remaining x velocity in the x direction, which produces this relatively small departure from the bulk result, from the no backflow result. And then you get you had somewhat strange velocity profiles in the crossing region, which then goes to the second order mode profile at higher wave numbers. It's interesting also to note that due to one of the roots of this characteristic polynomial, as I said, becomes quite large for larger values of qx. It's of the order of, let's say, 300 or something. So the square root of that is several tens of the units, of the length units. And this results in a very steep approach of the x velocity component to 0 at the boundary. So it forms sort of a boundary layer, but which is nothing to do with some non-hydrodynamic boundary layer. It's pure hydrodynamics that creates a rather thin boundary layer for finite values of the x component of the wave number. And so this is what the first mode does, and the second mode, of course, has a transition from this 2 nodes at the 0 wave number to essentially no nodes for higher values of qx. Now, odd modes, they do the same thing. They also avoid crossings with odd modes, but odd and even modes, as one should expect from symmetry, they don't mix, so they do cross. Now, experiments actually sort of is now in accord with these calculations. When one plots the expected dispersion curves for different modes, and these are the measurements done partly with differential dynamic microscopy, partly by light scattering. We see that we really observe expected behavior going, that we sort of cross from the one mode to the other, and the numbers come out right too now for the parameters. Now, what happens when we include weak anchoring? That means finite anchoring energy. For band situation and for qx equals 0 for pure band, that means again one can again in the same manner as before find an analytic expression for the characteristic equation. It essentially just acquires this additional term. So again, a very good approximate solution is very similar to what we got. It's actually the same as obtained with neglecting the backflow altogether. So when we used this 10 years ago, this is actually the correct expression to a very good approximation that one can use, even for the bend case, not only for splay and twist. Now, then again, of course, when you increase the qx, this will go to the expression that is expected from the bulk expression for the backflow. Now, for this mode crossing case with weak anchoring, so it's play bend and as a function of qx, the lowest order mode is now quite removed from the second or third mode, but we still get, this is still essentially a crossing, even though the splitting is quite large. And one can see that if one looks into the profiles of this first mode at small wave number here or at large wave number here, obviously it acquires this second order characteristic, and this second order mode acquires the first order characteristic like before. So this is interesting, even with. Now, it's a relevant question also. What happens now with the effective viscosity contribution to the relaxation rate when you apply an external electric field? In the bulk case, the electric field enters as a wave number independent contribution, E squared, of course, and this is rather helpful to analyze the elastic and viscous parameters by light scattering if you apply an electric field. So again, for qx0 case, one can use this analytic approximations, and now you get that the characteristic equation due to field gets this rational sort of expression being equal to the tangent of qa, and interestingly, again, to the lowest order approximate solution is again very similar to what one has without the field. And it turns out then, so this expression 6 minus this parameter beta, this is is close to, beta is between 0.9, let's say, to 0.5 in all realistic situations. So this is quite close to 1 times the rotational viscosity, but there is a small correction term affecting the field contribution, which is close to 1 but not equal to 1. So, and when you go to finite value of x component of the wave vector, you get similar. Then, of course, the calculation has to be numerical, but it's still the effective viscosity for the field term is nearly the same as for the elastic term. So that's what I wanted to say. So as one would expect for the fundamental mode, in all cases the backflow is nearly completely quenched, but there is some small change in the effective viscosity for the bent mode, for the relevant numbers of the Leslie parameters. Then, of course, at large QX, you always approach the bulk expression. We get this mixing and uncrossing of the dispersion curves for even or odd modes. In this case, going from planar to spline from splay to bend, and then both finite anchoring strength and field dependence sort of depend as one would expect, and except when if you want to be quite precise, then you have to take account of these small corrections that remain. Thank you.
Questions? So what kind of situation you have in mind? There is high temperature, all modes excited, or how?
Well, I mean, this is, I said that at the beginning, nearly invariably by light scattering, we look at thermally excited fluctuations, yes. So they're all, they're present.
What happens when you measure W this way? How does it compare with W measured by other ways? I remember in your last talk that you gave on the Bern-Splay compounds. Well, I was getting actually factors of 3 different for W.
For this,
I were using
in this particular, I mean,
B or something.
Since anchoring energy always depends on your particular surface that you have, it's very difficult to compare exact numbers for anchoring energy.
Look, I could take the same sample and instead of...
Yeah, that's it. I was about to say that. So in our particular case, we did take the same sample and measured the twist, this in-plane anchoring energy, the azimuthal anchoring energy, by applying a field in the perpendicular direction. This is sort of a usual way, and the numbers came out the same, yes. And the numbers that we get with light scattering, this is not the only, I mean, this is, we measured several cases. Then in Mushevich's group, they have also used these methods at some point to measure the anchoring energy. I think it's a reliable method, but I would.
Can I follow that up?
Yeah.
Okay. Now, one of the things that you claim that you might be able to measure is the surface viscosity, and Professor Virga here is on public record as saying that that the surface viscosity is not a consistent concept. Now, I don't know whether that's still your current position?
Well, I mean, I'm perfectly happy with that.
No, I was just wondering. I mean, because I was wondering whether, here you have an unambiguous method of measuring something that, on the other hand, at least one respectable mathematician says is not a consistent thing. So
I was careful. I was rather careful. I said that we have interpreted then this effective surface viscosity, I'm quite sure that this is what was happening there, as a mesoscopic contamination layer, either due to dangling bonds or dangling polymers from the surface, or perhaps even floating monomers of the orienting surface. So there we had some another case where we sort of claimed we have measured a surface viscous dissipation, and that was in the cylindrical cavities of nanopore type pores, of nanometer sized pores. We also got a term which was independent of the diameter of the pores in the light scattering data. I mean, of course, there are two kinds of surface dissipation processes which are in the literature. One is this sort of true surface viscosity, some dissipation mechanism which is in a very narrow surface layer. But then you have the surface gliding phenomenon, which is also kind of a dissipative process, but it happens on a very different scales for very different reasons. So sometimes these two terms are mixed.
Which implies the Lipid escape, the second mechanism.
Yeah.
Well, it's a very slow slipping mechanism, which is nearly surely due to absorption and desorption of the orienting layer, whatever that is.
So there's not an extrapolation length or something measure of how much you violate the non-slip boundary condition.
Yeah. On the time scales of seconds or even more than seconds, that surface orientation gliding doesn't show up at all. It shows in days or hours or something like that.
But you haven't actually, I mean, there's nothing implicitly in terms of surface gliding.
No, of course not.
But in principle, one could include that.
Not in this kind of a hydrodynamic picture. This is it's a
much longer time scale.
It's a very different time scale, yes.